In 12.4, we're going to talk about doing more graphs, but more specifically, rational functions. A rational function is defined as f of x, which equals p of x over q of x, where p of x and q of x are polynomial functions, and where also q of x cannot equal 0, meaning the denominator can't equal 0. These are going to provide us with graphs that are considered discontinuous graphs, and those are graphs with one or more breaks in it. And you'll see once we start actually doing the graphs what that looks like. So in this first question, what we're going to do is we are just going to graph f of x equals 1x. So let's start there. If you take a look at it, you can see that we have some asymptotes happening here. The graph comes up over here, and if you zoom out, you can see how it approaches this line, the x-axis on the right, and it also approaches on the left, and it approaches from two different sides. So on the positive y, when it goes to infinity, the asymptote approaches positive x-axis. And when y is negative infinity, again, it's going to approach on the negative x. You'll also notice, though, it has a vertical asymptote. So it just doesn't have one like we're used to, but 1 and 2, and we have graphs on both sides of those. Go ahead and copy the sketch of this onto the paper or onto the graph on the right. And then what I'm going to do, and you might want to use a different color pen or marker, we're going to graph f of x equals -4 over x. Now that graph is shown in the blue right there, and I want you to notice a couple different things. You can see that the blue is now reflected over the x-axis on both sides, and that has to do with the negative. So if I take away that negative, do you see how the reflection happens? So there's the negative, take it away, and we'll put it back in. I also want you to, let's get rid of the negative for a second, and I also want you to compare the red versus the blue. The red versus the blue shows at how far away it is then from that origin, if you can kind of see that. It 4 becomes a multiplier. And just like other things, you know, how it affects the height and the stretch of it, that is what is happening here. So on the red, you can see that the point where the arrow is, that's right going to be at 1, 1, if I can land it on there, right there. But if you go to the blue, it's 1, 4. So everything is kind of multiplied by 4 as you go out. So if I, go here, try to get that at 2. It was 0.5. I can get it again. And then right here, if I multiply 0.5, that should be about 2 then. So 2, 2. So all those numbers are multiplied. So let's turn that back. Then take a minute, pause the video, and make the sketch of this equation on that same graph. If we go to number 2, we have the graph f of x equals 2 over x plus 1. Again, this is considered a rational graph because we have a function in the denominator, as you can see that, as well as technically in the numerator. So we're going to see some asymptotes. I'm going to go back to Desmos, and we're going to start with that y over 1 over x. But now I'm going to compare it to number 2, which is 2 over x plus 1. And you can see that with the green. I'm going to get rid of the red for a second. And do you see how there is still a horizontal asymptote right there? So at y equals 0. But you'll notice the vertical asymptote shifted right there. And that's because of this number right here. So again, all those patterns of graphs that we've been talking about, they're applying to these rational functions as well. Because it's plus 1, kind of within this grouping, it's actually setting it to left. So it's setting it 1 unit. So then if I were to change this to, let's say, +4, it should move the graph over 4 units. You guys can see that. So instead of being at 1, now that asymptote is here. Go ahead and sketch that on that graph that you have on your notes. And while you're doing that, I also do just want to kind of take note as well about that 2 being a multiplier. So if I change this to 1, it's very similar. Let me zoom in just a little bit. And you can kind of see where these markings are, but if I change that 1 to 2, you can see how those extended out a little bit more. Now, if I were to subtract 4 from the outside of this, I want you to maybe guess what would happen. It shifted down, so the horizontal. So again, we're seeing those transformations of graphs happen with those rational functions. We're going to take a look at number 3, and I'm going to do this a little backwards. I'm actually going to go to Desmos, and I'm going to show you what this graph looks like first, so you can kind of get an idea of how it's changing. So if you take a look at this graph, this might seem kind of surprising. There's a lot going on here. You can actually see there's one asymptote happening right here, and there's another asymptote happening right here. And if we zoom in, you can see that asymptote happening at -3, and then at 0.5 right there. So we're going to start out this lesson to kind of show us how we can actually find where these asymptotes are without necessarily needing to see the graph first, but how we actually calculate it from the equations. There are three things that are going to happen. The first way is when the degree is higher in the denominator. So you can see this, it has an exponent 2 in the denominator versus an exponent of 1. If that happens, that's telling you that there is going to be a vertical asymptote, or at least one. And how you would find those vertical asymptotes is you would just simply take the denominator and set it equal to 0. And either using the quadratic formula, factoring, completing the square, because this is a quadratic, you would simply solve for x. This is factorable, so I'm going to factor this. And I get 1/2 and -3. Now I'm going to the graph right now, and you can see that's where that -3 was, and that's where that +1/2 was. Now there's actually something else that happens. Even though it doesn't happen with the entire graph, do you see how this line flattens out here and this line flattens out here, and there's asymptotes on these sides? So there is kind of an horizontal asymptotes happening, just maybe not all the way. And this is an example of a discontinuous graph where it doesn't necessarily connect to the different parts. So like the name suggests, it's disconnected from one another. So what we're going to find now is we're going to find where that horizontal asymptote is. Now, based on the picture we just saw, we're going to see that it happens at 0. But how would you calculate this? This gets a little bit trickier. To find the horizontal asymptotes, what you would do is you're going to divide each term by the greatest degree, or power of x. In this case, it would be x squared. So what happens is I have x plus 1, and then I add 2x squared, 5x, and then -3. And we're going to divide each one of those terms by x squared, so the highest power of x. And what you're going to do is you're going to see what happens as x approaches infinity. So basically, as x gets larger in each one of these cases, what's going to happen? So if I look at this first term right here, x over x squared, that's going to reduce to 1 over x. This one would just reduce to 1 over x squared. I'm going to come back to that in a second. This would become 2. This would be 5 over x, and then minus 3 over x squared. And again, I want to look at each of these terms individually. So let's just start with this first one. As x increases, so let's start with 1 over 1, and then 1 over 2, 1 over 3, 1 over 4, and so on. As I approach like 1 over 100, 1 over a million, and even higher, what happens to that number is it gets smaller and smaller and smaller. And what happens is it's approaching 0. So as it approaches infinity, this is getting closer to 0. Same thing with 1 over x squared. Now, nothing's really going to happen with that 2, so we're going to leave that there. But think about what happens as x gets larger for 5 over x. Again, it's getting smaller and smaller until it's going to get as close to 0 as possible. Same thing here. So what we end up having is 0 over 2, and that reduces down to 0. This right here is your horizontal asymptote, y equals 0. And you can see that happen on these two sides. So I'm going to do the same thing with letter B. I want to find my horizontal and my vertical asymptotes. I'm going to start with my vertical, and that's pretty straightforward. I'm going to take the denominator, set it equal to 0, and my vertical asymptote will be at x equals 3. Now, the highest degree in this one happens to be at x, so I'm going to take 2x, I'm going to take 1x, and then minus 3, and I'm going to put these all over, again, the highest degree, which is x to the first. And they cancel out here, so that reduces to 2. And then 1 over x, again, as x approaches infinity, so as it gets larger, this number is going to get really close to 0. This will become 1 minus 0. Therefore, our horizontal asymptote is 2 over 1. So it is y equals 2. Now, let's go to Desmos and plug that in to see what it looks like. And you can see it's discontinuous, and right about here, which is about 3, that's our vertical asymptote, and 2 is our horizontal. I'm going to do letter C backwards a little bit as well. I want to take a look at the graph to kind of show you actually what we're going to be finding. So if you look at this graph, it's pretty different than the ones we had before. It's still discontinuous, and you can see it has a vertical asymptote right here, but there's no horizontal, but there's a slant. This is called an oblique asymptote. And this happens when the degree is higher in the numerator. So this is going to give us an oblique asymptote, but you could still saw it gave us a vertical one. So we're going to start with a vertical. And again, we're going to set that denominator equal to 0. So we get x equals 5, and we saw that in the graph. I'll do a quick check to see if there is a horizontal one, even though we didn't see one. So I'll do x squared plus x minus 6 over x minus 5. Now, every one of these is going to be over x squared. And so that's going to give you 1 plus, and then this reduces to 1 over x, so that approaches 0. And then this approaches 0. And then the denominator 1 over x, that's going to approach 0 minus 0. Now, if you notice this is 1 over 0. That is undefined, so therefore there was not a horizontal asymptote. So where did this oblique asymptote come in? Well, here comes synthetic division again. To find the oblique asymptote, what you're going to do is you're going to use synthetic division, and I'm going to use my denominator, that 5 that I found. That's going to be the number out here. I'm going to do 1, 1, negative 6. I want to drop down the 1. 1 times 5 is 5. That's going to give you 6. That is going to give you 30. And then finally, this is 24. If you fill this in, this is x plus 6 with a remainder. We are going to use the asymptote y equals x plus 6. We're going to ignore this remainder for right now because this will be pretty accurate. And I want to go back to the graph. And I want to put in y equals x plus 6. And you can see that that's pretty accurate for where that asymptote is. It's approaching it. The green is approaching that line. Again, that's called oblique. We're going to use these to help us actually graph these by hand later on. Now, at the bottom of your page there is a chart that kind of shows you how you determine the asymptotes. It tells you how you find the vertical asymptotes and then other ones. So it tells you how to find a horizontal one and then also when to try to find an oblique as well.